Electrochemistry. We talked about electrochemistry last semester. We'll see how much you remember. But what's going on here is the backbone is electricity, right? You have two reactants, just like any reaction, and one reactant is producing electrons, the other one is accepting them, and it can get really complicated. But with that complication comes a lot of uses. I mean, we can get aluminum out of dirt, right? And that's pretty much why you recycle aluminum cans, by the way. It sucks up a lot of juice to get that aluminum out of dirt. And it's an electrochemical process. So since it's so energy intensive, let's just recycle, and it's worth it. They pay you for it. They pay you more in other states, but that's how it is. Batteries. Down below we have one of those supposed to be good for you vending machines, and there's apples in there. How do they keep them from turning brown? I'm pretty dang sure they didn't just slice those apples and put them in that box, because apples turn brown pretty dang quick. So what they may have done, I don't think they would have done this though, because you'd taste the lemon. So there's probably some acid on there that's going to denature that enzyme and to prevent the browning. So let's see if we remember a few things. Since electricity is the background, electrochemistry had its own terminology to try to keep track of these electrons and do some electron bookkeeping. And how we did that is we assigned every single atom in every compound in that reaction, reactants and products, we assigned them an oxidation state. So let's see if we can remember. These are the major rules. If you remember these, you can pretty much figure out anything else. The oxidation state that we assigned to oxygen in any compound, Erica's the one person who stepped out. Vivian was, do you remember what we assigned it? -2. I guess the only hint I can give you is that's the charge it usually forms on a periodic table, right? 2 over from the nobles. How about though, Allison, if we have any element in its natural state, so iron would be iron solid, aluminum would be aluminum solid, oxygen would be O2 gas. The oxidation number then, the oxidation state is always, what was it? Does anyone remember? It's the 0, the baseline. Right? I guess you should write 0. It looks like an oxygen. 0. When the oxidation states of all atoms present in a compound or ion are added, so you take all these oxidation states for everything in a compound or an ion, you add them all up, the total is always what? I'll give you some examples here. Carbon tetrachloride, the answer is 0. Sulfate, the answer is -2. Phosphate, it's always the charge. Charge. So you remember, what do we call these compounds that didn't have a number written up there? Start with the N. Neutral. We call them neutral, right? We didn't write a charge up there. Should be writing zeros, but we don't. Some more review. The thermite reaction is used to join railroad tracks. Let's take a look at that. A lot of these electrochemical reactions are pretty powerful. This one can melt iron.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron 3 oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon.
Metal burns. Isn't that crazy? It's magnesium. Definitely an exothermic reaction.
Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
Right? Now, why don't they do that in more cowboy movies? Right? That's pretty cool. but you know, when they're building the railroad tracks and stuff. Anyway, determine the oxidation state of each element in the below, that's the thermite reaction here. So let's just go from left to right here. Crystal, Zamora, how are you going to figure out this iron oxide compound? Where would you start? You need an oxidation state for O and for iron.
Well, O is always negative 2.
O is always negative 2. That's where I start. And I'm going to circle my answers. Monica, what's the trick to getting iron? They all these oxidation states have to add up to be what in this case? Have to add up to be 0. Okay? So you'd like to write, she says positive 2. You'd like to write that because then you get negative 2 and positive 2 is 0. But it's screwed up because we don't have 1 iron and 1 oxygen. We have 3 and 2. So our total charge on the oxygen is going to be a negative 6. So there's our oxidation state just for oxygen alone.
It's a +3.
Has to be a +3. Because 2 times a positive 3 is a positive 6. And that's how you get your answers. So just circling them is good enough. But if you want to go to the side and write iron's +3 and oxygen's negative 2, that works. How about aluminum? Diana, on the reactant side here, it should be what? It's just one atom. Add up all the oxidation states, has to be the charge. Well, aluminum would have to be what then? 0, right? Because there's just, it's kind of that rule where it's in its natural state, but you really don't even really need that rule. How about iron on the product side, Danielle? All right. +2, everybody agree? Yeah, because its charge is 0. You have to add up all the oxidation states and get the charge. Well, that leaves no choice. It has to be 0. Just like aluminum over here. Now we have something to calculate, though. Tegan, where would you start with this aluminum oxide?
The oxygen is always negative 2.
Oxygen's always negative 2. Keep going. Let's just finish this.
So the aluminum is positive.
Yeah. You hear? Because you're going to have a negative 6 over here. This guy has to be positive 3, because 2 times positive 3 is positive 6. So add up to be 0, because the charge is 0. Some terminology. Alyssa, when an element gets oxidized in a reaction, its oxidation state, how'd this work? It gets oxidized, so oxidation state gets more, it's more positive. Element gets reduced. We should have probably asked the reduced one first, because it makes more sense, Sabina, right? Because reduced means gets more negative. I should switch those for next time. Makes more sense. Oxidizing agents, oxidizing and reducing agents, Danny, are always, they're the institutes of change. They're the guys that are causing this to happen. They're the reactants. They're the agents. They're always reactants, oxidizing and reducing agents. The homework is going to expect you to figure this stuff out. What's the oxidizing agent? What's the reducing agent? Oxidizing agents, Crystal Munoz, they always get reduced. She remembers. And are always, everybody? Reactants. So everybody, reducing agents always get oxidized and are always reactants. Okay, so we have a reaction up there. We said reducing agents, Jasmine, have to get oxidized. Which compound up there is our reducing agent. And remember, we said it has to be a reactant. Iron. Iron isn't a reactant. Iron oxide is, and aluminum is. Anyone figure this out? Which reactant is getting oxidized?
The iron oxide. So the iron oxide has a total charge of.
Well, no, you could just look at each individual atom. For example, if you want to mess with iron oxide, look at O. O goes from -2 to -2. Didn't do jack. Well, check out the iron then. Iron went from +3 to.
So it gains electrons.
Iron went from +3 to 0. So iron got this iron oxide. It got reduced. So this iron oxide must be the oxidizing agent. So we should put it over here. Now, once you figure out one agent, you really don't need to go through and figure out the other one. We will, but the answer has to be what? Aluminum. It has to be the other one. So if aluminum is the reducing agent, Vivian, that means aluminum got what? Oxidized. So did it. It went from 0 to +3. So did it get oxidized? Yeah. That's right. Okay. Get rid of that. Write the unbalanced half reactions for the thermite reaction. The unbalanced half reactions for the thermite reaction. Remember doing this? Let's see if Allison remembers. How do you do this? How do you write a half reaction? Do you remember this? Remember, Gabby? How do you remember this? What is it? Fe2O3. Yeah. If you put the 2 out front, then you're starting to balance it. They just said unbalanced, so you just quit there. That'd be one of the unbalanced half reactions. Crystal Zamora would be the other unbalanced half reaction. Al going to Al2O3. Okay. 2 types of electrochemical cells. First, we have non-galvanic. They call them electrolytic. In fact, one of these, well, let's just show them first. Galvanic or, sorry, this is non-galvanic electrolytic, so I gotta click on it. Non-galvanic. The pickle light.
A pickle is incorporated into a simple electrical circuit. The forks provide contact between the pickle and the power source. Alternating current will be passed through the circuit.
So it seems to have generated some light there, Diana. Did it look like a natural process, or did they have to force that to happen? Yeah, they had to force. They're probably plugged into the wall or something, right? So delta G for this must be what? Anybody? Must be positive, right? Electrolytic cells, definitely not a battery, right? Okay, you got to force that stuff to happen. However, you would like to generate a battery. If you're on island, whatever, no electricity, ooh, let's generate a battery to charge my cell phone so I can call somebody and get the heck off, right? So get some lemons and dig up some screws, and you will be set.
This lemon battery is related to the zinc-copper cell. You can build this battery from lemons, galvanized nails, and pennies. How much electrical potential is generated by a 3-lemon battery?
Can you read it? It says about 1.5 volts. Now, if you've read your little batteries, which battery does this one match? Right? The AA. They're 1.5 volts. So you just made a AA battery. So literally what they did is they just jammed pennies and these, it has to be zinc-coated screws though. Those are the ones that are kind of shiny. Jam them in there and connect them up.
What about the wires?
Yeah, you're gonna have to find some wires somewhere, right? So you gotta, but you can, if it meant you to get off, you could find stuff is always floating up on the beaches, right? Use your earring things. I don't know. There's a will, there's a way. Okay, what are the half reactions in the lemon battery? So I don't know if you got all that out of there, but one of them was those had to be copper pennies. There is a lot of tricks to this because the pennies they make nowadays, is there a lot of copper in there? No, so you got to get pre-1968, something like that. And they're copper, pure copper there. But the copper is actually dissolving. So when you pull those pennies out, man, they're going to be really nice and shiny. You pull them out of that lemon. Then the other one, that zinc, when you jam those zinc screws in there, the acidity of the lemon is actually dissolving some of the zinc. So the other reaction, that zinc is actually redepositing back onto the zinc screw. So those are the half reactions, but they're not complete. We should really complete them. Monica, how do we balance these half reactions? All right? Now, we don't need to know all the steps, but it might be a good reminder. Do you remember what you had to do? First, you balance everything but O and H. Then you balance, now there isn't any O and H here, so we really don't care. But it's good to remind you all these steps, I think. What if you come up against one? Balance everything but O and H. Then you balance O's by adding H2O. Then you balance H by adding H plus. So balance everything but O and H, O by adding H2O, H by adding H plus. Then you balance charge by adding electrons to the most positive side. Those are all the steps. You really don't need them for all this because copper, copper, done. No O's, no H's. So add electrons to the most positive side. And how many? 2 of them, because then it'll be the same charge on both sides. So likewise down here, and you're done. Okay, that's how most of them are. I don't think you're going to have any complicated ones. We did that last semester. So what would it look like if we separated the lemon battery half reactions into 2 different containers?
A galvanic cell consists of 2 half reactions connected by a salt bridge and an external wire. In this example, a zinc metal electrode is oxidized to zinc ions at the anode, and Cu2 positive is reduced to form copper metal at the cathode. If the 2 half reactions are connected through a voltmeter, we can measure the electromotive force for the reaction. When connected to a light bulb, the current of electrons flowing through the wire causes the bulb to glow. The anions and cations flow through the salt bridge to compensate for the change in the charge caused by the electron flow.
Okay. So I don't know if you caught all that, but Whoa. Let me go back to that.
A galvanic used to form copper.
So what is the purpose of first off, the reactions are the same. What's going on in the lemon battery and what's going on here. The reactions are the same. It's just cleaner because they just have these nice beakers with the solutions in them. And what's the purpose of this salt bridge? Because we have the wires and all that stuff that makes sense. But I don't remember seeing a salt bridge in the lemon battery. Yeah, the pickle didn't have a salt bridge either. The pickle light didn't. How could it not? What does the salt bridge do? Yeah, it flows. It allows cations and anions to flow back and forth. Exactly. What physicists say, how they define charge helps me. Anything that has a charge and moving, that's current. We like to think of current as electrons. But man, anything that has a charge and moving is current. So you could have cations, anions, moving, that's current. Because if you want to light up a little light bulb, you need a complete circuit. So that's what this allows. Yeah, there may not be electrons like there are in the wire flowing in the salt bridge, but it's ions, moving charge. That's current. It works. The lemon battery, you didn't need it. The ions were right there. You jam that stuff in the lemon battery, it's full of ions, acids and other ions. So they're there. They're moving. The pickle light, same story. There's ions. You just jammed it in the whole pickle. There's ions in there that are free to move and complete the circuit. Okay. Let's see. By convention, the oxidation half reaction always occurs in the left cell in voltaic cell diagrams. Okay. Oxidation half reaction. Whoa. Which one of these is my oxidation half reaction? Top one or the bottom one? Everyone agrees it's the top one, right? My oxidation half reaction. They're going to call that the anode or the cathode. The only way I remember this is oxidation and anode both start with a vowel. For years, that's the only way I can keep this stuff straight, right? Anode and oxidation both start with a vowel, so that's anode's oxidation. So what the question is, electrons, by convention, they want you to put that anode on the left-hand side. So electrons are always going to flow from the left to right or right to left. They want the anode on the left-hand side. The anode is producing electrons. So those little electrons are going to have to flow from right there. We want to put here. We can start drawing it. They say put the anode over here. Right? What is the anode half reaction? It's got to be that copper solid going to copper plus 2. Right? So the cathode half reaction would be the other one. Oh, let's see. All right. If you start drawing this stuff out, which is what they want. I guess I'd like to have a little bulb or voltmeter or something. They'd like to do that. And then we'll put another hunk of metal. Okay, electrons are flowing from which side to which side? Yeah, because they're being produced over here, and they're reacting over here. So, good. All right, being produced, reacting. So they're going in that direction. And then we got to finish it. They want you to draw in like, okay, you have some copper +2 here. And this hunk of metal needs to be what type of metal? Copper solid. Good. This guy needs to be zinc solid. Needs to be in a solution of zinc ions. All right. What am I missing? My salt bridge. So my salt bridge. Okay. So we've got, I think we have pretty much everything we're supposed to have in there. We can circle answer up here. Okay. Name me a salt, Tegan. Give me a name of a salt. Sodium chloride. So this is a sodium chloride salt bridge. Okay. Someone mentioned the purpose of the salt bridge is to allow those ions to flow in and out of there. So what ions do I have in my salt bridge? I have Na with a what? +1. And I have Cl with a -1. Okay. Which one is flowing out of the side with the anode? Which one would it be? It'd be the Cl-. Why? Crystal's exactly right. Why? Because of the charge. We're producing copper +2. So the Cl- is going in to pretty much balance the charge, all right? But it's really flowing to complete the circuit. Okay, so you can look at it in a couple different ways. One way to balance the charge, the other way is, well, it has to complete the circuit. How about on the other side, where +2 is reacting? +2 is disappearing. So we're going to have what flowing out here? Na+, because look, we're losing positive charge. It needs to be replaced. So that's how things are played. So when the homework asks you to describe a cell, to draw a cell diagram, I think those are the only two ways they mention it. You got to go through all this. Okay. Hopefully there will be a lot of questions that say, nope, give me the shorthand notation or give me the cell notation. Oh, nice. Why? Because it's so much briefer. What they do is every galvanic cell has a salt bridge. So you represent that with just double lines that are really close together. So that's how you represent the salt bridge. Then all you do is pretty much look at the half anode. It has to be on the left side. Cathode has to be on the right. So pretty much look at your half reaction and write it in, except use a comma. So I'll have copper solid, comma, copper +2. The other side, everybody, I'll have zinc +2, comma, zinc solid. Okay, if they told you the concentration, 0.1 molar, well then you would write 0.1 molar or whatever it is, right? But they didn't, so I'm leaving it out. That's one thing. The other thing is that you replace the commas with one single line if it changed states. This is just how they do it. So did we change? What is this? So copper solid, state's obviously solid. What is the state for copper +2? Remember, we're lazy. We didn't write it. What is the state? It's AQ. It's aqueous. So did it change state? Yep. So replace the comma with one solid line. We'll have to do the same for the cathode. That's the shorthand galvanic cell notation. Much nicer, right? And cleaner. Okay. So go ahead and try this one. obtain the half reactions, and then describe a voltaic cell using these half reactions. So does that mean they want cell notation? If you want to match the answers in the back of the book. They said describe. Describe was the one with a lot of work, right? So you have to draw it all out. Make sure you put the anode on the left because you want to produce the electrons on the left. So I think that's about everything, right? For me, it helps if I write the half reactions below, because then I know what I'm doing. Okay, last one, and then we'll call it a day. Consider the voltaic cell. Write the half cell reactions and the overall cell reaction. Make a sketch of the cell and label it. Make sure you include labels, anode, cathode, direction of electron flow, that whole gambit. So if you want to write the half reactions, pretty much just replace these lines with arrows. You pretty much have the half reactions, right? And then add them up. Make sure you make the electrons cancel, and you'll get the overall cell reaction. Did you remember to cancel out your electrons when you got the overall cell reaction? You had to multiply one of the half reactions by 3, the other one by 2. That way I can get those electrons to cancel out. And just add them up. So there's a bunch more you can practice on. And come by. I'll be glad to work on this stuff with you. Be here all day pretty much tomorrow.